Hang with Madagascar. So the rate of growth, dp/dt, so dp/dt, of a population of bacteria is, going back to algebra 1, is means equals, proportional to the square root of t. All right, proportional means that it's following that model f of x equals kx. All right, x could vary. It could be a function. It could be just x. But in this case, that x value is going to be the square root of t. All right, so we're looking at k times the square root of t. All right, so this takes on the role of x, the x value, in our directly proportional set. All right, we don't like radicals. I mean, the concept of a radical is fine, just the notation. We don't like that because it doesn't lend itself too much to integral calculus. So dp/dt, let's make that kt to the 1/2. Right, now I have to solve the differential equation here. They don't say that explicitly, but it's kind of implied, because they gave us a rate of growth, but then they're talking about what the population is. So the population would be basically people, not people per year or people per hour or whatever. In this case, bacteria per day. We got to get rid of the days. The way to get rid of that is by integrating, right? And there'll be more elaborate discussion on that in the next class. I also have to talk to you about that. All right, so I'm going to rewrite this as dp equals kt to the 1/2 times dt. All right, so I'm multiplying through with the dt. Then I'm going to integrate. So p would be equal to, and last class we said that, yeah, it's p plus c, but that c is going to get moved to the right anyway, so we could just write the p. Right? What's the antiderivative of kt to the 1/2? Kt to the 3/2 over 3/2, which we'll clean up in a second, plus c. And we're only going to clean it up because it serves our purpose to clean it up. All right? We need to do something with this. It's going to be better to just have it in a cleaner form. All right? So p would be equal to, keep change split, 2/3 kt to the 3/2 plus c. Say it again? It will just be a number, but we're actually going to solve for what that number is. And it'll be fine.
I thought that proportion of relationship between two variables, not between them.
No, it's between two variables, but its relationship is some numerical constant coefficient of the other number. So it's not like, if here's one proportional relationship, x is y. But if x is double y, that's still a proportional relationship. So as x increases, y increases. So that's what the purpose of the phasor is. It's a multiplication factor that allows the two variables to be equivalent to one another.
So life is a constant, right?
But it is a constant, yep. So the initial size of the population is 500. So what that's telling me is that when t is equal to 0, p is equal to 500. So I'm going to pop that in. So 500 equals, if I'm plugging in a 0 for t, that whole first part is going to zero out. 0 plus c, which is just c equals 500. So I can say that p equals 2/3 k to, times t to the 3/2 plus 500. We have two constants built into, well, one that was built into the equation and one that came through the process of integration. the constant of integration c, we have to figure out what both of those are. Now you can see here that that first condition was only able to give us one of the constants. So if you have two constants, you need two conditions. Right? If you have 10 constants, you need 10 conditions. Right? Unless something miraculous happens where everything zeroes out. In this case, they gave it to us. They said after 1 day, the population has grown to 600. So I'm replacing the p with 500, and then I'm replacing the t with 0. So this whole thing zeroes out. So 0 plus c is going to become.
So you
Yeah, it's just a continuation of the previous step. All right, so now I know that when t is equal to 1, p is equal to 600. So I could say 600 is equal to, so I'm plugging in a 1 here. That cleans up, I mean, not as nicely as the plugging in a 0 would clean up, but it cleans up all right. Replace the t with a 1. 1 to the 3 halves is what? Yeah, it's just a 1. If you multiply that by 2/3 k, it's just 2/3 k. Plus 500. Alright, so we substituted into these two guys, and that gave us this, this continuation. So then we could solve for k. And what do we get for k? Mm-hmm. 150, yep. So then putting these two equations together, well, I guess they're both equations, but these two ideas together will give us our particular solution, and then after that, answer the question. So if I plug in a 150 for k here, I'm going to double it, get 300, divide by 3, so it becomes a 100. Alright, so you're just plugging and chugging away. 2/3 times 150. Because k is now known to be 150. Question. We're plugging the k into this guy. So we're getting 2/3 times the 150, which is going to give you 100. Everything else remains the same. I'm just plugging and chugging away. And then the last step is just to replace the t with the 7, because I have p equal to all this stuff, but if I want to know at t equals 7, then I'd be looking at 100 times 7 to the 3 halves plus 500. And you get some approximate answer for that. Oh. I'm going to make this smaller. Hide large display and close this up. There we go. So 107 raised to the 3 halves plus 500. So 2352-ish. Approximately 2352 bacteria. That's gross. Initial size is 500. I mean, I guess I've seen more invasive. Oh yeah. A lot of algebra. And so actually go back to what we were doing here and just kind of reflect. I always like to find the calculus as like the where's Waldo. There it is. I Found it. Right there. Not calculus, not calculus. One instance of calculus. Not calculus, not calculus, not calculus. No, none of that was calculus. Alright? So, and that's not even, like, crazy calculus. That's just reverse power rule. So,
Interval of 0 to 10.
it ended up not mattering in this case. But if I were to say something like, find the amount of time it would take to have 1 million bacteria, and then you came up with an answer of 15 days, then you would say no solution because it doesn't fall in the domain.
Okay.
Oh, I found the elevator problem. I was wondering where that went.
No, before it's stopping at.
Fun fact, time works its way in. You actually need to figure out at what time it is at a velocity of 0 in order to determine what floor it would be at. So it's in there. It will. There will be. There actually, if I'm not mistaken, are two answers to this. One, because there are two instances in which the elevator comes to a stop. One is negative and one is positive. So if you just look at it in that regard, you can say, oh, it was at rest before it got to me. But because it says will stop, it's implying future. So you would disregard the negative anyway. But that's the question. So I'll put a star on that one. I want you to enjoy that one. Number 5, this is actually the last thing that we're going to do tonight. I'm only going to get you set up on it. I'm not going to do the whole thing for you. It's just the verbiage in the opening there is a little much. According to Newton's law of cooling, the rate of change in the temperature of an object is proportional to the difference between the temperature of the object and the temperature of the surrounding medium. So you're supposed to make an equation out of that. Like if you don't have any experience with Newton's law of cooling, that takes you a second. A 12-ounce glass bottle of liquid is placed in the freezer that's kept at constant temperature of 20 degrees Fahrenheit. The initial temperature of the liquid is 70 degrees Fahrenheit. After 5 seconds, the liquid's temperature is 50 degrees Fahrenheit. How much longer will it take the liquid to decrease to 37 degrees Fahrenheit? All right, but most of that stuff kind of works itself out. It's this part. So let's take a second here and digest this. All right. So we have temperature. We have a bunch of things. Temperature of an object. Temperature of the surrounding medium. All right. So we're going to let T be the temperature of the object, capital T, and capital T with a little sub n, little subscript of m. That'll be the temperature of the surrounding medium. That's how we're going to denote it. Lowercase t is always time, so you can't mess with that. All right. All right. So it's saying the rate of change in the temperature of an object. Rate of change. It's talking about a derivative. All right, because that rate of change would necessarily have to be moment by moment, not over an interval. At any given moment, there is a change in temperature in a particular object. So that's our license to call it a derivative. So the derivative of the temperature of an object, T, with respect to, I would imagine, time, because at every instance when they start actually asking us questions, it's initial temperature, so time t equals 0. After 5 minutes, how much longer? Those are all measures of time. So the rate of change of temperature of an object per unit of time is proportional, assumed directly, to the difference between the temperature of the object, which we're calling T, and the temperature of the surrounding medium, T sub n. And it gets messy, but most, I mean, it won't work unless some of this information is given to you. So, temperature of the object is going to vary. We need to figure out what K is. We're going to get a C once we integrate. The T sub n is the temperature of the surrounding medium, but that's constant, they said it. The freezer that is kept at a constant temperature of 20 degrees Fahrenheit. So that T sub m, while we denoted it as a variable in our equation, is actually given. So that's this guy right here. So dt dt, d capital T d lowercase t, is equal to K times capital T minus 20. So it's the rate of change, which means derivative. So the derivative, so replace the words rate of change with derivative in the word, in the sentence. The derivative of the temperature of an object, so capital T, because that's how we're defining it, has to be an implied relationship to time, even though it doesn't say it there, because they're asking us about time later on in the problem. So d capital T d lowercase t is equal to, because it's proportional, we follow the model kx. So I got my k. The x part of it is the difference between the temperature of the object, which we're calling T, and the temperature of the surrounding medium, which we're calling T sub n. Alright, so just follow. The k comes from the rule that's above in the previous question. It says directly proportional is f x equals k times x. No problem. So, I need to integrate this somehow. When you integrate, you want to have consistency among your variables. So, what I want to do is I want to get all my capital T's over to one side and all my lowercase t's to the other side. So, first thing I'm going to do is cross multiply. I'm going to have dt equals k times t minus 20 d lowercase t. Okay, that's the first part of the process. But again, I want like variables together. So you see that binomial is capital T minus 20, that's got to go. Because it can't be associated with a d lowercase t. Otherwise, the integration process doesn't have the same meaning that we need it to have. So I'm going to divide out the t minus 20. So cancel, cancel. 1, I'm going to write it as 1 over t minus 20 dt is equal to k dt. So now I've isolated my variables. My capital T's are together, my lowercase t's are together. Well, there were no other lowercase t's, so it didn't matter. And that k can stay on the right with the lowercase t, or it can go to the left with the capital T. It doesn't make a difference. But now we can integrate. But that's the point where I'm going to leave you, because I want you to try that part of it on your own. All right? You may or may not be successful based on prior experience and knowledge. There are some facts that are going to come into play in the solution to this differential equation that if you just don't know those facts, you might be in a jam. But I want you to try it first before I spoil it. If this ends up being like that's not working, then number 6 is definitely doable. Right, so that's where we're going to leave it for tonight. And we'll pick up with those problems next class.